Yes. Nobody wants to come see a programming stream on Friday night. There's only 9 viewers. Hello. MIT lectures on quantum physics. Certainly a reasonable way to spend your time. Certainly a reasonable way to spend your time. What's up, people? Wait for the Atlas hot mess. I don't know what that is. Is that a game? Thousands are watching Twitch streamers not play Atlas because it's been delayed again. This is a pirate MMO from the makers of Ark. From what I heard, the people who make Ark are not let's just say I wouldn't be friends with them. We'll wait a little bit more for people to show up before we start getting serious. Let's get our tools on deck. Let's get that out. Bam. And then wait, what? Oh, the telemetry builds I didn't fix. Certainly didn't fix all the indentation goofs. All right. All right. Bam. Have I ever met Arndt? Yes, I did a long time ago. Do I use any tools like Lex or Yak Bison to help with the compiler? No. Is the Lexing parsing code all written by yourself? Yes. Tools like that will not help you. Not in the long run. All right, I'm going to close Discord. So what else is going on? Any questions before we get started? Questions? Questions? What is telemetry? It is a profiling tool. We showed how it works on a previous stream, but we're going to do it today as well. I could use some more light in here. What's the speed up goal? There's no specific goal, although, as I'll explain when we start, I found something really obvious that we should be able to get a decent perf speed up with little work, but we'll see. You got Braid on sale from GOG. The jumping with a space bar is maddening. I guess you have an inconvenient space bar. You want to jump with an up arrow? Well, later in the game, you'll see why that's not a good idea. Some people put jump on Z. I don't remember if that works in Braid or not. It might. I don't like games. I don't like platformers that jump with up arrow. It's bad sauce. Also because it overloads with climb. So how does the game know if you want to climb or jump? It guesses, sometimes wrong. Jumping with up arrow is very European. Okay. Well, that game was not made in Europe. Well, I think there's enough people here for us to get started. So, let me drink a little bit more. So, it's been a long time. Hold on, my voice is really, I don't know what it's doing. Maybe I should drink something warm instead of something cold. Rust can now execute arbitrary code at compile time. Well, that's good. I'm glad to see I can influence people, but it's still not going to be as good as what we do. Time for some frothy milk? No, because I am out of milk. Okay, I'm going to make a warm drink, and then I'll have that option, and then we'll start. What are those books about? They're about many different things. Many different things. Okay. Well, let's get started. So, for a while now this year, we shifted our work priority off of the compiler and mostly toward the game. So we've been doing a little bit of compiler work. Well, I'll say I've been doing a little bit of compiler work. There's other people on the team who have been still spending most of their time on the compiler. But for me, I sort of shifted off that onto the game simply because the game is the real application of the language so far. It's our one real serious program, and so the more serious it is and the further it is in development, the more we really see whether the language is meeting its goals and so forth, right? So last time, I don't remember what the numbers are, but last time I demoed anything on the compiler was at this speech in Barcelona, and I think the game was like 80,000 lines, something like that. Maybe it was 90, I don't know. Now it's 106,000. And as the number of lines of code have been going up, the compile time has been going up as well. And in Barcelona, again, it was like 0.8 seconds. Now it's like double that for much less than double the code. So there's something super linear happening in the compiler that we are triggering. And I've just decided not to worry about that for a while, because even though compile times take longer than I think they should, our eventual goal is to be at least an order of magnitude faster than this. Right now, it's about twice as slow as it was. Well, that's a little bit of a bummer. But this is still an amount of time that doesn't affect workflow that much, right? Like 1.6 seconds to compile a 100,000 line program. That's still faster than just about anything else. Certainly in terms of new high-level languages, it's much faster. But you can't slack forever. And so today I decided it's about time for me to shift back and start doing some serious compiler things. Abner made a fuzzer, and we found some bugs with the fuzzer, and so I went through and fixed those. There were some crashes in one infinite loop that I fixed today. So he's going to run the fuzzer some more. And I'm going to start doing more big features. But before I start doing more big features, I want to work on the speed here a little bit. Oh, and I also sort of got one of the final ideas I needed for how to parallelize the compiler fully in a way that won't drive me insane and be super complicated. That will be a major restructuring of the program, so I'm not sure on what schedule we're going to do that, because it might be more important to do features first. But I finally figured that out, and I'm very happy with that. No, there's no big announcement today. This is a work stream. A fuzzer is a program that throws a random and potentially hostile input at your compiler, like not programs that aren't necessarily trying to be correct or useful, but that try to stress test the compiler and get it to fail. And hey, we got it to fail, and then we fix the failure. How do you fuzz a compiler? Well, there are a number of people out there in the world who have done good work. Just search for that question on Google. How do you fuzz a compiler? And you'll see. Okay, so, our amount of time to compile has been slowly creeping upward. And before dinner tonight, I just did a little bit of profiling. Let me just close this again. So let's write down about what our total build time is. It's like 1.65 seconds, in that neighborhood pretty consistently. So I'm going to write that down, because if we can improve that by the end of tonight, that's pretty good. And I think we will, because like I said, right before dinner, I spotted something that really looks like low-hanging fruit. So instead of the release build of the compiler, I'm going to run the telemetry build. That's a build that's instrumented for this profiler called telemetry. And we're just going to run that. And bam. So it's a little bit slower, right? It's 1.78 instead of 1.66 because of the overhead of profiling. But then you get this very nice and detailed display of what your program was doing. These are all the different job threads that are like loading files and parsing them and stuff. You can see that even though we parallelize the compiler, most of the work is actually still serial right now. So this is kind of the thread that we're mostly waiting on. And while we're able to spread out some of this work and reduce latency, it's not lexing or parsing that takes the most time right now. It's the type inference and subsequent phases. And so, we don't get to parallelize any of this yet. And when I said I have ideas for restructurings, those will eventually help us break this into pieces that can then be done simultaneously. All right, but for now, that is not the case. So we have to look at why things are taking so much time. And when we're doing type inference, one of the things that we do a lot is look up identifiers. And that calls this function find in block. And if you zoom into one of these, you'll notice that we spend a lot of time in find in block. So I was like, what happens if I just, this gives me sort of a more traditional profile view. And wow, find in block is the top routine, just looking up identifiers. It's 355 milliseconds, right? Which is, 1/5 of the compile time right now. So something's going wrong there. And so I looked up, what does this code do? Because I thought I made it fast before. Let me find where it is. All right, we'll go here and we'll go to declaration. Oh, go to definition. Yeah. So here we have this thing, and it's just looking in this members array and matching the name. And I'm like, that's weird, because we did this whole thing where we can convert blocks to large lookup that has a hash table so that we don't have to iterate over the members. And as far as I can tell, either I did all this work and then forgot to use that table, or I put that in and then it got deleted somehow, or I failed to check it in. So I don't think we're using this hash table at all. So if I look up large lookup table, oh, here we do in find declaration helper. So this is where we set it. So obviously we're looking up things in scopes, not through find declaration helper, I guess. This is weird because like this looks like exactly what we would wrap the thing to. Maybe I was just not quite done with it back then. Yeah, telemetry is made by Rad Game Tools. It is a commercial profiling product that they license to game studios and other developers. But yeah, it's super good to be able to just zoom in on your program and just see exactly what happens. Super good. And you can control what these colors are and what strings go here. So sometimes I annotate the data, like maybe if I go down into the parsing here, maybe not. I don't know. Some of these I give additional information that you can read, but I don't remember which ones they are. So this is interesting. I want to know who calls find in block. And should I just... So there's preload scope. We call find in block. We call it quite a few times. I'm wondering why I didn't just have find in block say, hey, if we're a big scope, do this thing. And I wonder if the answer is that there was a reason or that I was just being conservative. So I think we're going to switch to debug build of the compiler for a bit. What was that called? Large lookup table, right? I'm not sure why we have a flag and a pointer, but we do. Okay, so here I'm just going to say, I have a feeling that we're calling this for large blocks, but let me just put an assert. What's it called? Large. This is the flag. I have a feeling if I put this assert in that it will fire. Right, so we're going to run debug build. Oh wait, I compiled it before putting the assert in. Dude, C++ compilers are so slow. Yeah, so we asserted right away. So let's just put in our thing from down here. I'm just going to say if this, like why didn't I do this, right? Else, if it's not large, just look things up in the array. If it is large, equals find name right. Like I think that's it. Table. I see. All right. Well, let's just run the debug build and we'll see if it complains or fails or does anything wrong. It appears to have compiled the game. It appears to have run the game. Let's start the game on a good level. We're working on Mirror's Island. Whoops. There we go. Let's start there so that we have something nice to look at instead of my stupid programmer level. Yeah, IntelliSense is really bad except for the one thing which is good, which is that you can right click on things and say go to declaration and go to definition, except that sometimes that doesn't work correctly. Okay, let's do release build and see if we saved any time with that. It's not a foregone conclusion that we saved time. 1.28 seconds. 1.27. All right. So 1.65 minus 1.27, that's almost 1/4 of total compile time we just saved. Ship it. Let's run tests. I guess I just forgot to do that. So now you'll notice that there were some other things that were like hard-coded for the large lookups. And, uh-oh. Unable to open examples, libsvn, svn underscore. This is just our... I think I have a junk file in there. Like the test thing like looks in all the folders and tries to... I should have run. I wonder if I broke something. It's possible that I broke something there. That only one of our tests. SVN update, SVN info, SVN revision. Weird. We might have broken something. I don't know what we would break. Let's see if that's a consistent fail. At this point, it could be anything. There could be a bug in the program. Could be a bug in the different part of the compiler that only exhibits sometimes. Could be, like I said, a spurious file. Huh. Huh. Interesting. Okay, like the string is truncated here. Unable to open file im. Why is the string truncated? Let's turn that thing back off for a second so we can see if it's this or if it's something else. This is what I get for not running the tests first before we do anything. I was running the tests during lunch and it was fine, but I might have broken something during lunch. Sup, hummus? Okay. Well, I think this did break something because when I turn this optimization off, we have no problem. And when I turn the optimization on, which I'll go do, maybe we do have a problem. But that just means, well, we'll find out what it means. I don't think there's any reason why we wouldn't be able to do this. But what it means is maybe the large lookup table is not in sync. Or something like that. Or maybe there's a thread safety issue. That's always possible. It's always possible. Okay, so does this fail? It seems to take a lot to make it fail. But we're really motivated to figure it out because it's a quarter of compiled time. Now it's succeeded. But now it failed. That's really interesting. Like, I don't exactly know why we would end up, like, it's printing out the name correctly here, and then I believe this. This looks like to me, and I'm not sure, it looks like to me one of those bugs, like I seem to remember very vaguely a bug like this that would happen in very rare cases. So it seems to me like a bug that is not directly related to what we're doing, because I don't see exactly how it could be, except that maybe it's being exhibited more often because we've changed the memory access pattern or the order in which things retire in the compiler or something. And what I suspect is the following. I suspect that the compiler just isn't making its own memory when somebody calls add build file. I suspect it's not copying the string or something like that. I'm going to look that up. And if it is, then we'll print out, or if it looks correct, we'll print out the string that gets passed to add build file. And if it's too short, then we know that the bug is on the application side and we can go. I'm actually not sure that this is by add build file, but we'll try it. So add build file. Well, we copy the string right there. Okay, let's just see. If that's truncated, then the problem is prior. Otherwise, it's post. It could be that we copy the string, but then we accidentally write a 0 into the string. Why am I adding build file with nothing? Because it's... No, not that. I wanted this 2C string. It's going to leak some memory, but we don't care because we're going to delete it. All right. Now we're seeing it. We're seeing add build file. Rename the company to Cloud Imperium Instant 500 million. Okay. Oh, wait, this is coming from the command line. Right, this is printing out commands. So this is like from Josh's thing, and I guess... Right, or no, this is... Okay. Yeah, this is coming in on the command line. So our add build file doesn't work. That's very odd. Let's just break when that... Oh, it's going to be hard. How do we... Like, I never know if Windows is correctly set up to, like, open the debugger on an whatever interrupt. What is the best way to debug this? Well, let's just verify that by application startup. Okay. So I'm just going to check. We're just going to check that that is fine by that point. And that's just helping us binary search. Does this corruption happen before that point or after that point? And that'll tell us something. Or it could be a Heisenbug that just stops happening. Oh, wait. This thing... We're running release build of the compiler here, so I have to compile release builds. I thought I took out the add build file thing. Why is it still printing it? Because I didn't. Okay, well, it succeeded. It could be a Heisenbug. Let's run a few more times. I mean, it's certainly not happening the majority of the time because we're compiling all these things and it just is tripping up once in a while. Yeah, see it. It's something that's very sensitive to memory layout, I think. We might have to dig deeply into this one at some point. Yeah, see? I added a printf, and it's not happening. Four in a row. Is it a Heisenbug or is it due to the randomness of multi-threading? It could be. It could be a thread safety thing, but in principle, I wouldn't think so for this. I wouldn't think that this is thread safety. I'd recommend that you find which specific test it fails on most often and run that multiple times. I don't think it's a specific test. It's failing in the thing that launches the tests, right? Like this thing, you know, puts together a string to exec, right? Like it execs the compiler name with some arguments. And then the compiler runs, and when it tries to load the file in that argument, it's truncated. Yeah, see, now it's fine. It's fixed, ship it. That's what open source people would say. Works on my computer, man. All right, well, this doesn't really help me. So when we put together a standard debugging library for the language, I'm going to have a routine in there that's like, set up a debug breakpoint on this string so I can tell if it ever gets modified, you know, like a data breakpoint. We will have a user level data breakpoint library. So you can just put that in your program. It'll be baller. Baller! I think this bug has been there for a long time because I remember something like it. I don't know, man. I'm tempted to just keep working on speed and then try to pin this bug down in a separate stream just so that I don't get too waylaid in one spot. Now it's just not happening. My hard drive is warmed up. Yeah, we're going to have to hunt this down at a different time. It is a very important bug to hunt down. But there we go. It just started happening. Can we get it to happen again? Nope. Maybe I just got very unlucky right there there we go. Okay, well, what happens if I try putting this back in? If this makes the test pass, I'm just going to check it in with the printf and a comment that says, we're going to say compiler bug, this seems to change timing so that some race happens less that involves corruption of the file name to be loaded. This makes it hard to debug. I'd like to find a user level data breakpoint library or something like that. Okay, so we're gonna do that on a separate stream. I'm putting on my piece of paper Heisenbug. And right now we're going to keep working on performance. We'll run the test one more time. It could be even a compiler bug for all I know. I doubt it, but it could be because, like, you know, maybe the fact that this uses this quantity causes the compiler to not do something that it otherwise would do. Maybe it's a UB situation. Compiler writers are so annoying. All right. Make compile time 0.4 seconds faster. Going on, that makes the okay, boom, ship it, sort of. Run it in a while loop. Have I run address sanitizer on the compiler? I haven't. I don't know if the other guys have or not. We should definitely do some ASAN. We should definitely do some TSAN. On Windows, we don't typically compile with Clang, but on Linux, I think we do. So that would be a good spot to do those things. All right. Let's run another telemetry build. And I'm going to leave the old one in memory here so that we can compare. All right. Well, I don't quite know where to look. Let's look at the traditional like ranked profile first. Oh, not there. There. So this has like everything in this and all children of this, which is sort of everything on this main thread that we're waiting for here. Prep type table, 100 milliseconds. Why is that so slow? Infer types, I believe, like, okay, that's doing the vast majority of the work that the compiler needs to do. Even then, it's only a quarter of a second. Lambda body print disassembly, that's starting to get low. This doesn't actually print a disassembly. This is like emits x86 machine code, so it's a little bit of a misleading name. This is messaging. Oh, wait. This is 358 milliseconds. So like, this is spending a lot of time. We're going to have to look at that at some point. Okay. Yeah, 80 milliseconds in its own body. I'm not sure that's very good. Polymorph. I know how to make a lot faster. That's part of that big compiler restructuring, but it's not really that close to the top. Yeah. What should we look at here? Let's look at prep type table. I want to know why that takes so long. So one of the things, so the type table right now contains every single type that could possibly be in your program, and this prep type table generates the version that'll go in your executable. Now the thing is, you don't actually need most of those. You only need types that are queried by your program, which, you know, what those are actually known statically. So we could actually flag the things that your program needs to know. The thing is, we would need to like recursively flag, because like you know, if you want to know the type of some procedure, or let's say the type of some data structure, well, that data structure has types of its members and so forth. And so we would have to like recursively flag things. However, that's not necessarily that bad. So that's a thing that we could start doing, if not completely do tonight. I don't know how much of this 100 milliseconds it would save, but I am guessing a reasonable amount. It just might not be totally trivial. And right now I'm not sure whether I just want to be looking at time or whether I want to just start attacking things. Wow, messaging is getting slow. Send messages and do export. These two things, this is a quarter of a second. This is just telling your program about what are all the data structures. So I'm a little bummed that that's taking that long. Although again, in principle, this could be done in parallel. Yeah. Yeah. All these things can be parallelized. I don't know. You know, whenever I start profiling like this, it's just I start looking at a giant screen of numbers. And there's just numbers everywhere, and you never know what to really pay attention to. I had actually thought that polymorph would be much higher, but really it's not. So type table is big. This is kind of big. This is just outputting x64 instructions for all the bytecode instructions. So a way that we could attack this number is to look at the bytecode instructions, for example, and see if we're emitting too many in some cases and cut down the number that way. That would actually get us a win here and in bytecode generation. So even though this number is not that big, you might be able to, you know, double your gains. So we have 88,000 types. That's large. Oh no, we have call. Okay, this includes times that we suspend because something's not ready. So we don't have 88,000 times. Okay, never mind. Never mind. Let's actually. I want to break in prep type table, and I just want to know how big of a type table are we talking about. I'm feeling like maybe we do this type table flagging thing, just because I've been thinking about that for a while, and so sometimes maybe it's just time to do the things you were thinking about. Okay, so oh, this is already packed. Wait, what? Okay, this isn't what I thought it was. This is when we're taking what the type table gave us and then putting it into the object file, which we're like, the thing is we have to remap all these goddamn pointers. So if we made them be relative pointers, this would go faster. But also, if there weren't as many types, this would go faster. So the question is, when we fill this buffer, wow, it's like 45 times. It's 3 megabytes of data. So it might be that find or create symbol is slow. But let's also, okay, hold on. What is this called when? It's been a long time since I've looked at this. Like, where does this get filled up? Prep. Oh, type table packer is a different thing. Pack data for type table. Okay. Is that here? I guess that happens beforehand. The similar names. This is pack data for type table. That's prepared data for type table. Let's just say, forget how to do this. We say TM zone, TM function. So this will just add a profiling zone. So pack data for type table. We want to know about that. How much time does that take? Because if we make this do less work, then we'll save time here and in prepare data for type table. So let's look at this one. So we call find or create symbol. These are only twice, though. That's not going to matter. Like, this does a copy. It must be in finish type table and write relocations. That's the only thing here that looks like it takes time. Let's put this. So we're going to look at that. Because this just has a bunch of loops. Bunch of loops. And I'm not sure. Wow. All right. Let's just look at how much time those things take. Oops. Yes, those are signed 32 and 64-bit types. Okay. Boom. So this is our third profile, right? So we want to look at, whoops, this one. We want to look at, finish type table and write relocations. Way up there. It's the top frickin' thing in our entire program. Okay, and then pack data for type table is down here. That's 26. Why is this so much slower than like writing out the data in the first place? Is there something about... I mean, yeah, I'll be happy if we do a lot less work on the type table, and maybe we should just do that. But I want to investigate first why 100 milliseconds, that's almost as long as it takes to open a new tab in Chrome. It's almost as long as it takes to type a character in Atom. So we gotta know why it takes so long. It might be that this initial size that we're picking is very small and we keep copying our buffer as we expand. Copies are maybe not that expensive, but... Oh no, we're not doing copies because this is bucket size. This thing is bucketed, so we're not copying. Let's just set a breakpoint in there and just see. I bet it's a large ass number of relocations. So initial number of relocations is 71,000, which is more than I would like. 244 Lambda patches, 40,000 deferred type info pointers, 30,000, so it's like 70,000 pointers. So it's like roughly 1.5 millisecond per 1,000 pointers. That doesn't seem that fast to me. Oh. Here's the thing. These modify 8Bs. Okay. Okay. I bet most of the time is in modify, and I'll tell you why. We're going to measure it. We're not going to guess, but this concatenator, so that you don't have to do string copies every time your buffer ends up longer than you thought, this thing is bucketed. All right? But every time we call modify, we have to find this inside this buffer, right? Like this is an index as if it was a packed together string. So every time we call this modify, the concatenator has to find the memory for it. So it has to start at its initial bucket and then go forward until it finds the one that that contains the memory that we want, and then it overwrites that memory. There's two things we could do about that. One is we could try to like do some memoization in here. Two is instead of saying position in buffer, we could actually save the buffer pointer because we know that doesn't move. But let's measure it. Inline, inline, inline. Do we even call like modify 1B? Oh, that's 8 bytes, not 8 bits. Yeah. All right. I bet that's what's slow. Oh, that was debug build. Nope, telemetry. Just use an array in dynamic programming. Could use a bucket hint of sorts. Well, we could maybe just store the pointer to the frickin' bucket. Or we could just store a pointer to the memory, because the concatenator isn't going to move the memory unless you do something that would make it the data you stored in it invalid anyway, I think. So, well, let's find out. Okay. Oh yeah, we got a lot more profiling overhead here. Like if you profile things that get called a lot, you start adding a lot of overhead. Modify 1B is called 800,000 times, but you can't necessarily believe, like the fact that this instantly shot to the top doesn't necessarily mean it's the slowest thing, because, well, I mean, how long per call is this? 844,000, what's 200 milliseconds divided by 844,000 is like 1 microsecond per, or 4 microseconds per call. Which one, right, is micro 1/1000th of a milli? I think it is. But that includes overhead. I don't know how much the telemetry overhead is. Right, so modify 8B. Okay, here's the issue. We can't quite right now unless we change the concatenator a little bit, we can't right now just save the pointer. And the reason is this 8 bytes could be like crossing a bucket boundary, I think. Oh God, we just call modify 1B, yeah. So this is lazy balls. That's why modify 1B gets called so much, bro. This was all written just to work and not necessarily be fast. So it's time for us to make this be fast. I'm happy with that. Like this is an overstatement of the overhead here, but it's not that big of an overstatement. So these all call modify 1b, and modify 1b is the thing that it calls seek, right? Seek. Oh, we have these unchecked versions. I guess I implemented those for the machine language thing. Where we just assert that we have the space left, and then we write it. So really, we want to change to unchecked versions, like, yeah, see, so here I add unchecked things, and the reason is, like at the top of this loop somewhere, I called ensure space, ensure at least 64 bytes. So anyone down here can add up to 64 bytes without worrying about running out of space, right? So we want to do something like that. Now for a relocation, for a COF file relocation, you actually know the size of that. So we can ensure the size of the relocation, and then we can do add unchecked and modify unchecked, except there's probably no modify unchecked. Yeah, there isn't. But we will then be able to take a pointer to the thing and not do all this nonsense, right? So this is like endianness, and yeah, this is just a bunch of work that doesn't need to happen. Okay, we have a plan. Can I point you to a doc that explains the mission for this new language? Not totally, but as soon as I get off my butt, which is happening imminently now that I'm getting caught up on things, I'm going to write an intro message for our website that Abner's been working on and do a final review, and then we'll put it up. I'm hoping we can do that before Christmas. Yeah. Okay. Is 1B not inlined? It probably is. I mean, it probably says to inline it, but it doesn't matter that much. I mean, it's inlined, but like, dude, when your code looks like this, it doesn't matter that much if you inline the thing, because you're doing all this work. All we're trying to do is stomp down an 8-bit number. That's all we're trying to do. Okay. Back in a second, and then we'll get into trouble. Okay, so I'm gonna do this ensure space thing here. So here we have this get bytes per relocation that we can call. So we can say ensure space Of course, actually, right relocation might already be unchecked. Where is right relocation? Okay. It's not how I would have done that, but whatever. We've got plenty of bigger fish to fry. Right relocation cough. Yeah, okay. Okay, look. Ensure space 10. All right. We're unchecked. We're unchecked. We're unchecked. Okay. We're ensuring space 24. We're unchecked. We're unchecked. We're unchecked. Okay. So that will give us a small amount of speed, but not really everything that we want. But we're gonna build for a bit after each step here and make sure that we can at least build the frickin' game every time. All right. Seems to be compiling and running. We don't seem to have gotten a noticeable speed up from that, but I'm not that surprised because it was only like 70,000 things. We only skipped 70,000 checks, not that much. Let's run the tests. If we get our Heisenbug, I'm going to ignore it. Yeah. Okay, so that's pretty okay. All right. So now, when we do these modifies, we want to add them unchecked. Like anything that requires anything that could add a patch, we want to add it unchecked, which means we reserve the amount of space first. And then back here later on, we just want to stuff the pointer with modify 8b unchecked. Okay, so type info lambda patches, those are in type table packer. There aren't that many of these. Remember, we looked and there were like a few hundred. I'm writing down to not forget this. Okay, there were a few hundred of this one. These ones, there were 30 and 40,000 respectively. So deferred type info pointers and where is C coming from? I can't search for C. Oh no. Here's the problem, is we're modifying this after we've put it into our buffer. Which means we've done a copy, and whatever memory locations we save are not valid anymore. What we would really rather do is stuff those values into the memory that we know that we can stuff quickly. And then do the copy. So this is starting to get slightly more hairy, but let's look. So finish type table and write relocations. So packer offset. That's in prep data for type table. Oh, it happens right before this, okay? So I'm going to check in because we're about to do something that could go horribly wrong. We're going to say tiny speed up due to uncheck relocation addition. Speed up. Okay, I'm going to revert this so that it stops bothering me. Okay. Okay. So there's not really any reason like okay, wait. I thought we were putting the type table in its own section. Anyway. Oh my God, there's so many damn patches. There's more here and here. It's okay because this is everything that the linker does. We're just doing it instead of the linker. That's why we don't sit there and link for 20 minutes. Aren't the compiler flags allowed noise to be printed for every text? Test. It's just a big block that will be glazed over. Well, you know. You know, man. I thought we put the type table into its own section, but that is quite possibly not true. Maybe I've just been thinking about doing that. Ideally, you would like it in its own section just because you could see how big it is easily by looking at the object file. Let's just see. to see where we're at when we get here. Nope, we're 400K into some other section. Like, it kind of bothers me that I don't know what section we're in. Like, I guess it's in the same section as the code. We should genericize that at some point, but you know, even if we decide to put this in its own, the reason I was thinking about is it in its own section is maybe this is just 0, but I think we want the flexibility to put this in its own section or not. So this could be 0 or it could be non-zero. I think we're fine either way. We just track it. The thing is, we do not need to I don't understand why this is correct. Wait, oh, we do, okay. We do start a new section here. This is, okay, so this offset is not the offset within the section, it's the offset within the entire output file. That is why I was getting confused. Our offset within the section is 0 right now. We do make our own section for this, right? Okay. Then whatever the type table packer gave us as like, here's the data for the type table, we copy it, and then we do these things. I don't think there's any good reason for us to do this in this order. Except for what I said here about we may be using the type table memory to run, but I don't think we can. Like the type table packer is a different, like we just decided to do it differently from that because the version of the type table that we will have at compile time needs to legit have every type in your program because you're inspecting your program and you want to know what type everything is. Whereas, like I said before, the executable only needs to have the types that could be queried at runtime, which is a much smaller set. And so in the interest of being optimal there, we don't want this to be the same data that we're running with. Yeah, we just add zeros in here and it's all good. Okay. So for these patches, we're actually, instead of saving an offset, we're going to save a pointer directly to the memory. And then after we fill the memory in, we're going to do this copy afterward. Okay, so we're going to do this and that. Now we write relocations first, then copy the data over so that we know the target memory for the relocations is not split by bucket boundaries, so we can just stuff the numbers in there. Okay, that's a really wonderful comment. I'm sure I couldn't possibly explain that any better. So So we do that, and then we do this, okay? So now we have to go change this. This is fraught with peril right here. So any of these modifies now, we need to take out packer offset, I think. In fact, I'm going to change this to I don't even think that's valid to not put a star there. Oh, there we go. Yeah. Okay. So this is giving us errors every time we try to use this variable. That way we can be sure that we're not using it from this routine anywhere. Little tricks that you learn. So we're going to change all these modifies. Crap. Packer offset. Okay, this packer offset actually needs to be there. Oops. Because we're writing this relocation section that happens like, so what we're, every relocation has two parts. In the target memory where this pointer is going to be, you save the relative address, okay, of the thing. And then you save later a relocation that tells the linker or operating system or whoever, like, hey, at this offset is this relocation that needs to get turned into an actual pointer when you load the program, all right? That needs to have this packer offset there. So we do need to refer to that variable from in here. But this one, these modifies do not. So the modifies, instead of saying C, we're going to say, damn it, my mouse is running out of battery again. This is packer buff. Let's say packer buff. Not packer bug, that'll curse our program. So these modifies are all in the packer buff. General local pointer patches don't. You need to modify the value. Okay. Had to plug my mouse in for a while and get bad mouse feel. Okay, add and maybe steal. Okay. Okay. We're doing all these at once now because we have to. Okay, so packer offset. Okay, this is, yes, the relocation, relocation, relocation. That's a totally different place. All right, so maybe this works. What's it called? It's called C. Nice, terse, KNR style variable name, which I don't usually do, but in rare cases, for some reason, I do. Hey, well, we compiled Sokoban. It's not really any faster, but it's not supposed to be faster yet. Not yet. Okay. Great. Let's run the tests. We'll check that in, and then we'll do the thing that will hopefully make us faster. Bilbo Baggins was a survivor. All right. Prep for faster pointer stuffing. Okay. So it turns out the only one we gotta do is, or we gotta really worry about is this one. Because this one there's not that many of. We'll do it anyway, but this one there's not that many of. This one doesn't modify because we already knew the relative address at the time when we made this, right? So it's just deferred type info pointers that we need to deal with. So what we want to do is instead of saying modify 8b, we just want to stuff the frickin' thing. Yeah. And we're going to want to byte swap 8 or something. Okay. Here we're going to say well, this deferred type info pointer, instead of having a position in buffer, it's just going to have target memory. So we're going to go, instead of doing this, and we're not even going to do the little endian yet. We're just going to say star target pointer equals this. Just straight up stuff. That is a lot faster than all these instructions that we're running for this frickin' thing. All right. So, but deferred type, that's a type info patch. Okay. S64 star target memory. We are relying on the fact that the memory doesn't move, right? Okay. So, well, let's just see who errors, because people are trying to set that. Position in buffer is not a member. Line 45. Okay. Ensure space. Okay. We're going to say ensure space and return pointer. because this is going to return us the pointer to the space that we wanted. Return, well, I don't frickin' know. The current bucket. What do we do when we frickin' add? Last arrow point. Okay, well, here we want to say deferred dot, what did we call it? I don't even remember. Whatever is ensure space and return pointer 8. Really, usually when we do this, we want to put a 0 in, so maybe we'll combine all that later. This might be over abstracted, but who cares? It's not called position in buffer. It's called target memory. All these routines can be sped up, man. Like here, we're just making something on the stack and then copying it when we add it to the array. We could do an add empty and give us back the pointer and then fill it, and we would skip the copy. Like, oh, yeah. Anyway, so who else is complaining? Cannot convert from void star to S64 star. That's fine. Oh, we called it target pointer instead of target memory. We just can't decide target memory. Right relocation does not take 4 arguments. Position in buffer is not a, yeah, okay. Okay, one at a time, one at a time. Type table packer, line 45. Void star, no, S64 star, blah. Okay. Right relocation. Position in buffer. I think we want both. All right. Well, who knows what's going to happen? Anything could happen. That's why we're just going to go straight to a release build and have a party. Hey, look. It worked, and we saved some time. Look how much less. We were like at 1.27. Now we're at 1.16, 1.22, 1.16. Bro. Uh-oh. However, our value, our output is incorrect. So we're fast, but we're broken. Okay. That's okay, though. We can debug that. So one thing I can do so first of all, we can toggle this back here. If this works like it did before, then we can do this and then assert that the memory hasn't changed, right? We'll see. We don't know what's happening. Okay, game doesn't run. What the hell, people? Windows ain't done till Lotus won't run. Awful. Terrible. What did we mess up? It was so easy. I mean, let's just do it again. We're going to do it one step at a time. We're just going to revert. Sometimes we do that. It's like when you're learning Kung Fu and you're like, oh, you screwed up your thing. Start over, buddy. Start over. Do it right this time. Someone says they saved me 58 minutes. Maybe not. All right. Rebuild. It still doesn't work. Really? What's going on? Did I not run Sokoban? Oh, now we got the Heisenbug. Oh my God, everything's crashing down now. The tests all run. Okay, so we didn't correctly run test Sokoban after doing this change that was about when we reordering the buffer store thing. So let's back that one up. Right? So this one was just switching around the order of these. Oh, and removing packer offset. Okay. We're going to do this really one frickin' thing at a time. Yeah, here's the other differences. Okay, let's revert that and make sure that runs. Because if that doesn't run, we need an even better back in time potion. Okay, we've got a window. We've got a game. Yeah. Okay, so the first thing I'm going to do is literally just oh, I guess I can't really do it smaller. I can't really do it smaller. Okay. Let's try again. What was it called? Finish type table and write relocations. Okay, we were doing this beforehand, which was there, and then we're adding the data and adding the symbols. Okay, let's just move the symbols. That's an incremental thing. This really shouldn't matter. I sync. If it does matter, then we have a surprise. All right. And if it doesn't matter, if it works, then we've narrowed down what we got wrong. Let's see. Can I change to fill rect with the black brush so it's not a blast of white? That would not be a bad idea, but it's off topic for now. I don't want to derail. You're going to get a blast of white, a blast of amazing, brilliant color every time the thing opens. Okay. So we're calling finish type table and write relocations, and the theory is that I can move this to after so long as I also change my index here to not use Packer offset. And, well, and to not use C here, right? This is Packer C, right? Packer C. Okay, this is wrong. This is wrong. Okay. The thing is, we're starting to take addresses of things before we've actually added this. That's the mistake. We didn't look carefully enough. Whoops, compile it. You can't just run it. Uh-oh. Uh-oh. We're screwing everything up. Oh my God, we're screwing so many things up. We're never going to have a working compiler again. It's just all going to be broken. So you know what? We're just going to steal. We're just going to steal. So instead of just adding, we can do this thing where we just chain these buckets on the end. And that leaves the memory the same. So then we could even do it in the order that we're doing it. Let's try that. because I wanted to do that eventually as an optimization, but like if that clears up our problems now, then let's do it. So definitely steel. Okay. So we do this, we write the symbols just like we did. And you know what? If this doesn't work due to me moving too many things around, we'll frickin' do it again. We're just moving these back to where they were. If that's wrong, we'll do it again. We'll do it as many times as it takes. We will do it as many times as it takes. Definitely steel. Takes a different argument. We just took a name for that. What are you doing? What are you doing? Okay, I don't trust that, but whatever, we'll try it. Still not working. Oh, because we took... Okay. Okay. Let's revert again. We're reverting again. Gonna do it again. Oh, we don't want to revert because that'll mess up our undoing of, because if we revert to head, we'll get the updates that we pushed back. Okay. It doesn't, we could do that again too, but finish type. The problem is this thing here. Let's delete this dumb comment. Okay, see. Oh. Okay, this was definitely wrong this time. Like if you're going to write it into the packer, we had to take out the packer offset, and we didn't do that. So that was wrong. This might be right. It might be closer to right. It might be further from right. It might be orthogonal to right. Oh my God, we compiled. And we ran. Okay. So I'm going to check this in as fixed our screw up. And then we'll go back again and do the memory pointer thing that I did. Okay. 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 Great. Commit. Fix our screw up. It was chat's fault. Not really. It wasn't chat's fault. It was my fault. Have I seen Zig's error system? No. I'm not really interested in error systems. What do they do? Okay. Now, here we're going to go back here. We know that we want this position in buffer. Target memory. Ensure space and return pointer on C. Can I show the water again? It's off topic. We're working on the compiler, man. How come when I work on the game, everyone's like, when are you going to do a compiler stream? And then I do a compiler stream and everyone's like, let me look in the water. And I'm like, the water's not even done. It's going to look way better later. Why don't you just wait till the water's good? Like, oh my God. It is. It's humans. No, I mean, anytime you get 200 people on a stream, some of them are going to be interested in one thing and some of them are going to be interested in another thing. You're always going to hear, like the people who are seeing exactly what they want to see, it's not going to say anything. You're going to hear from the people who are like, what is that other thing that you could do? Okay, so now we've added this pointer, but we're not using the pointer yet. All right, so look, you're going to see the water again. Oh God, let's not show the water for too long. It's not done. Okay. So okay. Instead of this modify 8b, we're going to say stuff it. Oh, we had our comment before. Let's comment that. What? How did I get over here? All right. Now we got a stew going. Now we got a stew going. Yeah, I should be able to work on an infinite amount of things. Yeah, it's like when people say, when are you going to make an operating system? And when are you going to build a laptop? And I'm like, dude, look how fast we are now. 113, 115. We started today at 165, a full half a second. We have sped the compiler up by half a second. Well, let's make sure this runs. We have sped the compiler up by half a second today. It's all been low-hanging fruit, and there's a lot more low-hanging fruit. You know. That's enough time to type like 3 or 4 characters in Atom. That's how much we sped up the compiler today. Okay, so we want to do that here as well for the Lambda patch. Actually, oh, you know what? I bet the LLVM backend might look at these. No, it does its own frickin' LLVM ass slow thing. Okay. So we want to do the same thing here. Let's do that there, just for avoidance of doubt. And then we could even oh, we did the steel memory. We did the steel memory. Insert Reddit people saying that because the compiler is faster, there must be a trade-off in runtime speed. Oh, there must. Just keep believing that, suckers. I'll point out this is single core performance still, all right? And we're going to be way faster than this by the time we're no longer single core. This single core, well, mostly single core, on 100,000 lines. Jerks. We're not even, this low-hanging fruit that we just did, there's like 10 things like that before we even have to get serious. Okay. Like there's so many stupid things like that. And like I said, this type table is still almost all of the data that we're putting through here is data we don't even need to put through there because the runtime program doesn't query it. And maybe we'll start on that tonight. I don't think we'll do that whole thing tonight because it's going to get late. And that's a big change that you want to be fresh and awake for. 10 million lines of code, multi-threaded development, machine time target. 10 seconds. Let's look at telemetry again. Hold on. That's a target. I'm not promising that we will definitely hit that, but I'm hoping for that. Computers are fast. Computers are fast. Okay, we're doing this Lambda patch. Target memory, add unchecked, Lambda. Okay, again, this won't matter for speed because like there aren't that many of these, but we're doing it for uniformity and etc. So the Lambda patch. Oh, and we have to do the endianness as well. Someone remind me to do the endianness after we test this. Okay. I don't know why everyone gets excited about water in games. It's just one of those things. People are interested in water in games. All right, what are we at? Our official number is like 118, 112, 115, 114. We'll call it 115. 112, 113, 128. Our compiler decided to do something there. Discord like burped. We'll call it 115. do a little bit more here. So there's a general optimization that I could do a lot. So like I said, I'm making this thing on the stack, and then we're just adding it to this array. And I could, well, let's, oh, we got to do the endian. Got to do the endian. We got to do this. If we're not little endian, byte swap 8 it.target memory. We're not really going to be able to test this right now because we're not on a little endian machine. But at some point, we will, of course, vet everything on a big endian machine. At some point, we will vet everything on a big endian machine, so it's fine. Okay, well, I kind of wonder, there's probably other places that modify 8B a lot. Like there's all these frickin' data segment patches. When we run telemetry again, we might see a lot more modify 8Bs. Like look at all these. Some of those won't matter because they're one-offs, but anything in a loop could potentially still be a problem. Okay. Okay. Let's just make sure we didn't screw something up real bad. Okay. Add lambda patch direct memory stuffing endian condition as well. Whatever. Sometimes my commit messages are not the best. Okay, I just want to do this. I want to say dot add empty or dot add uninitialized. We're going to have that, and we're going to say auto deferred is this, or let's say patch. So the array is just going to give us the final memory as opposed to us filling out something not final and then copying. It's going to give us the final memory, and we'll fill it in. What? There. And we're going to do the same thing. Type info lambda patches dot add uninitialized. Yeah. All right. Let's make sure which array this is. We have several arrays. Yeah, it's just this one. So, this is a T star add uninitialized. Okay. Unable to match function definition to an existing declaration. What? This is where initialized. Oh, I put the parameter. Do a full recompile. That's a good idea. That is a good idea. But first, let's make sure this appears to work. Okay, didn't really affect our compile times in a massive way, but that's just one to have in our back pocket, you know. Uh-oh. We frickin' broke it. How did I break it? Bro, that was not a hard thing. I mean, apparently anything could be a hard thing. Add uninitialized. We didn't change the order of these things. Oh, no. Okay, we didn't increment the number of items in the array. Duh. I am a freshman college programmer. So, that's what we needed to do. It's much better if you can query your brain to know what you did wrong as opposed to starting a debug session. Looking at compile speed, we're looking at how much time the compiler takes and reducing that amount of time. We already sped up the compiler by like 30% tonight. That said, you know, it had been getting slow for reasons that are, you know, just, you know, sometimes you do early versions of the code and you let it sit around until it becomes a problem. And that's sort of what's happening to these things is, you know, these things were done in order to, oh, Heisenbug. We're going to have to debug that maybe tomorrow. I don't have a good idea for what's the right way to debug it. So I will need to think about that. Okay, well, array add uninitialized. All right, that's great. Let's do a full build as has been suggested in chat. Just because when you modify headers and stuff, you can't really trust Visual Studio that well to have cleared out all dependencies and whatever. And also a debug build, because there could be asserts on variables that we removed or something, and those don't get compiled in release. All right. Ta-da! All right. 115, 115, 116. All right. So let's do a debug build. Make sure. You'd start with sanitizers and try and figure out if any one compiled program causes it to crash more often. Yeah, I don't think it's really any one program. I think it's just some kind of race condition, probably. But I don't know. It must be a race condition combined with... Like, I'm just not sure what would cause you to write a 0 in there relatively consistently. But I think maybe we'll just do a whole thread about hunting that down. Or maybe not. Maybe if it's easier for the other guys to do on Clang, maybe I say, hey, guys, take a look at that. And then let me know if you can't find it. Okay, so we did that. So I want to run a telemetry build again. And I suspect we might still see some more modify 8Bs high in the profile. And if we do, that's great. If we do, actually, because those are probably also easy to get rid of. And we can make the compiler even faster. Okay, so we're going to run the telemetry build. Boop. Boop. All right, 132. Close that one. Oh, not settings. All right, so wait, 160. Oh, did we roll over to 9 p.m., 9 p.m., 8 p.m., 11? It put it up at the top instead of the bottom. I don't know why telemetry does this sometimes. It confuses me. Oh, because we went from 9 to 11 and 1 is before. It's sorting lexically, not like by number here. So it's a little annoying, but not the worst thing. Yeah, we reduced, so zones here is like the number of zone markers that we go through. We go through 500,000 fewer zone markers because we got rid of all those modify 8Bs, which were clusters of 8 modify 1Bs. Just a lot of killer Bs. All right, so let's do this view again. Okay. We've got modify 1B is still being called 500,000 times. Modify 8B is 40,000 times, which is 300,000 of these. So I feel like even though this isn't totally at the top of the profile, it's worth still looking at. Can I jump to like, I don't think I can jump to modify 8B from here. Can I? Can I like click somehow on this? Let's see if we could find it. This is in object file writing. So this is way over here. Modify. Well, those are modify 4Bs. Oh, so I bet this is all, this one is all 8s and 4s. And both of those are probably optimizable. Okay, but apply symbol patches, 70 milliseconds. Okay, this is the area that we were just optimizing. Prepare code. Was it? Wait. Yeah. Because everything we were doing was after emit code. This is a long time, 140 milliseconds. We're going to have to hit that. Like, what's going on in here? We're just calling modify 8Bs. Yeah. Modify 8B, modify 1Bs. Look at those. That's in symbol patches. Line 2201. This is not going to have a huge, you know, if we cut 30 milliseconds off of this, you know, that's like 0.03 seconds. But those add up. You do a few of those and they do add up. I mean, 0.03 is a lot. I mean, in a video game, that's a long time. So, you know. And it looks like that's basically all. Dude, we're just calling this modify 8B. This entire thing is modify 8Bs. Look at this. Look at this. It's a solid wall of modify 8Bs. Okay. Line 2201. Do I vtune? I used to use vtune a long time ago, and then it seemed like it got unusable or something. So I haven't tried in a long time. Is that ImGUI? Well, it's an ImGUI API, but I don't think it's like Dear ImGUI. I think it's RAD's own code. But the fact that it's responsive and fast and actually updates as I move tells you that it's not like Qt or anything like that, or Windows GUI or Mac OS. Like that, those things just don't operate this quickly. So it's like real code, not any of that crap. Okay. So it looks like this is the only modify 8b in there. So, yep. These are called symbol patches. I assumed that I could do the same trick and just put the pointer and make sure the memory doesn't move. Target adder, it.pointer location. Yeah. By the way, for people asking, like, what does a linker do? This is basically what a linker does, and we're making it as fast as we can make it, right? I mean, linkers do other stuff too, but most of that is unnecessary or wasted work that undoes other wasted work. Really, and even most of this is wasted work because, again, well, telling it where the pointer is wasted work. I don't know. If you just change some things about the way we load programs, it would go a lot faster. Let's just put it that way. All right. Symbol patches. That is a symbol patch. There are 3 places where it gets added. You know what? Let's do that add uninitialized first. No, let's do it second. Symbol patches add uninitialized. Okay. So here, we're going to do the same thing here. We're going to say code patch. We are relying on the fact that memory does not move. And we're going to say this. Equals there we go. Okay. So this is going into a buffer called code, and That is just our output buffer. We just named it that for this routine. Okay. These are going to be a little bit challenging. Not super, but like anytime we call this routine, this one or or this other one. This rip relative symbol patch we don't need yet because we're only doing 8-byte absolutes right now. Whoops. I wasn't looking when I did that. Okay, so adds here, and then is 8-byte absolute. Where was that one? Add patch for entry point. Actually, even this one doesn't need, okay. Oh, that's an entry point patch, not a symbol patch. Okay. Okay, this is actually the only routine that we need to do. Yeah. Yeah. Position, section number, position within wait. We only have one overload of add 64-bit symbol patch, and it's not this one. Position, section number, right? This is like not even a thing anymore. Bro. Yeah. So these are, of course, erroring because we didn't modify it, but none of them take a string name anymore. What? That must have been some slow code. All right. Add 64-bit symbol patch. Pointer. We're just going to say that. Pointer. Actually, let's not call it pointer. That's too generic. We'll call it target memory because that's what the other thing is called. Target memory. Okay. It's 4 calls. Type table base patches. I mean, I'm actually not sure what happens here. Wait, this is not the call to that. That's a different routine. Wait, what? Oh, no. It is. Okay. Okay. Pointer, undeclared identifier. That's target memory. All right, we have five things to do. And Emacs decided to delete half my file, just like I wanted it to. Okay, so symbol patch gets void target memory. Actually, so I'm going to write down symbol patch always has target memory set. Yeah, vector doesn't mean growable array unless you're in dumb bad names for things C++ land. And everybody who inherited that, which I guess includes Rust now, great guys. Way to be mathematically illiterate. All right. I am in that land? Well, I'm trying to get out of that land as fast as I can. I don't use vector to mean that. No, I don't. I use vector to mean vector. I do not use it to mean array. That's just not what it means. It's not what it means. What would I call a growable array? I'd call it an array. Or an automatically growable array. C# calls a growable array list. Yeah, that's not great. Dynamic array, that's fine. Dyne array, that's fine. Stretchy buffer, that's fine. What is not fine is vector. Gare, that's fine. I mean, I wouldn't know what that means if I read it, but at least I wouldn't think that it's something that's closed under addition and scalar multiplication. Next, Rust for Games programmers talk will conveniently skip over that very obvious point of confusion. Yes. Thing that holds multiple elements of the same type and will allocate space as needed. That's a totally fine name. It's better than vector. It is better than vector. In contiguous memory. Yep. Okay. You could like bind that really long name to a function key in your editor and just slam it all the time. It would be great. Okay. What am I even doing? I've been reading chat instead of programming. Okay. Okay. So I need to be able to get a target address for these things. So the problem is this is like scary. Okay. This is scary because any of these could be wrong. So we're going to keep this old thing. We're not going to change over to stuffing it yet. HR puff and stuff. Let's just look. This is coming from the type table. I don't quite know the ramifications of that. This is literal pointer position. This is going right into the end of the buffer, so this is fine. Target memory. Ensure space and return pointer 8, right? Then we put a 0 there, just like we always do. We could have this also say 0 at whatever. Oh, actually, no. We don't know how long this instruction is. Where is it? x64 instructions. Move 64 immediate into register forcibly 8 bytes. 1 to 10. Now we're getting into dangerous business. Now we're getting into dangerous business. We could use an abstraction to make this less error prone. 21 December 2018. Okay. So the +2 is to skip over the instruction bytes and go to the address bytes. Very volatile. Possibly the move 64 call just returns the address we want. In fact, you know what? Let's just do that. Let's just frickin' do it. See, we were doing something that where dependencies were kind of spread out between each other. So anytime we do this forcibly 8 bytes thing, we're going to return this. Okay. And then we do that. Great. Move immediately into register forcibly 8 bytes. Do that. Same thing right here. That was a good idea to structure things that way. Boy, same thing here. Wow. Same thing here. Bro, I think we're a winner. We're a winner, winner, chicken dinner. We might have one more. Ensure space. Oh. Okay, we're missing one. This one that I didn't know what to do about. Okay. So type table base patches. Where are these? I assume it's in the type tables thing. Base patches. Type table base patches. What are these? Offset from start of type table. Position within buffer. Oh, look. Look. It's our buddy. We're doing the same thing everywhere. Bro. We have too many patch types. At some point, we're going to have to simplify this, but okay, we're going to have some casting problems maybe. Maybe that's not the best place to cast. Okay, so we're not actually using these pointers at all. I just want to make sure we still run. We do. We're taking a little more memory for patch to store these pointers, but it shouldn't really affect our runtime. Except we're over 115 a lot. All right, well. Okay. Okay. Prep for more patch optimization. Optimization. Okay. Well, target memory. Where were we? Here. Okay, here's what we could do. We're going to say other is this assert other is equal to this thing. So that way we know when we flip it over, got to run in a debug build. But we know when we flip it over, well, let's see if the assert goes off. That's all I'm saying. If it goes off, we did something wrong. We won't know till toward the end of compilation. Takes time to get there. Oh. Its target memory is null. Baby. How'd that happen? How did that happen? No, it's not null. It's C, 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 C. And the reason it C's is because we don't always return a valid value here. Oh, no, we do. C, so C, 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 C means it was a stack value that was cleared, or that it was never set. It was declared on the stack, never set. Okay. So I might have missed a place where symbol patches are added. That's commented out. That really should have, let's check the constructor, but if that didn't, no, this is initialized to false, so otherwise we would have bigger problems than we have if that weren't true. This is the one that we got. What's this one? But it's false, because we don't set it to true. So I'm confused. We must be doing something real bad with this pointer. Oh, you know what? We're not setting target memory to pointer. We went through all this and we just never did it. And my spider sense was tingling because I was like, we should have had more patches from Void Star to S64 Star, and we didn't. And I made note of that, like, that's troublesome. And that's why, because we never frickin' used the value. Sometimes people ask me, how do you get into the games industry, right? How do you do a good job? How do you publish an indie game and make trillions of dollars and get on Steam? And I say, use the value that you pass to the procedure. If you don't use the value that you pass to the procedure, you're going to have a hard time getting into the Steam top 27 games, new and upcoming. It's true. You can think I'm joking, but it's true. Do I prefer working on language or game dev? They're both fun. I've been mostly focusing on the game for a while, but I'm going back to compiler stuff for a bit, as you can see. Okay, so since this assert is true, we should now be able to do this. Let's debug. Oh, you know, let's try running the frickin' game that we compiled from debug build. Let's make sure that works. Because even though we didn't assert, it's not a foregone conclusion. All right, let's compile again from debug build. Actually, I don't think this makes an executable. Oh no, it probably does now, because we got rid of all the stupid Visual C++ environment variable requirements, although I'm not sure. Let's just release it. Can you make it big in game dev if you call arrays vectors? Well, I don't recommend that, but I'm pretty sure that some people who call arrays vectors have made it okay. 1129. The sad thing is all this time I'm saving right now. The like 0.4 seconds that we saved at the start is for all the builds. But now the things I'm doing only make our x64 backend faster and not the LLVM backend. So, you know, Ignacio usually uses the LLV. Let's run tests, and we'll rerun if we get the Heisenberg. Can you program PUBG if you call arrays vectors? Oh, yes. I'm sure you can. Oh, yes. All right. Yeah, Heisenberg. We keep getting that. We got to fix it, but not right now. All right. Okay, what's our numbers looking like? 112, 117. Oh, big difference. 112, 113, 113, 118. Oh, we're getting noisy, man. 1125. Let's call it 110. Let's call it 113, just to be a little conservative. All right, we started at 165. We're at 113. We sped up by over half a second tonight. I mean, again, it's low-hanging fruit, but whatever. So now when we run the telemetry build, we are still going to see... Wait, did I commit? I think I did. I'm starting to get tired, so I'm not sure if I want to do more of these tonight, but we'll give it a try, and if I break it, we'll just revert. We're on hour 3 of the stream. Hour 4, we're at the top of hour 4 on the stream. Let's run the telemetry build. We'll get a new timing. I think I accidentally ran the telemetry build a couple times, so we're going to have a lot of profiles sitting here, but we can close some. 1140. Let's just... We don't need to compare these. We're living in the present right now. Okay. Okay, let's do the sham bam bamina. Okay, where's our modifies? Oh, modify 8B. Modify 8B now has more self time than modify 4B. We have so many fewer of them. Remember when we had hundreds of thousands of these? Now we don't have hundreds of thousands. But these are still, we have hundreds of thousands of modify 1Bs. Oh, I guess we never had hundreds of thousands of these. We had like double what this is. Well, I mean, these should be almost completely free in all these cases. So I say we just keep curb stomping them until they're gone, you know? Like this, and this, and this. Just do some curb stomping. Could do the easy add and initialize non-patches. We could. It's on the piece of paper though, and I don't think in terms of overall time that's that big of a deal. It's like this is bigger. But yeah, you're right. If I feel too tired, I could just do that. That's a good point. Some statistics test to see if you have sped things up. Yeah, I mean, if you were going for serious optimization, you would run over a larger corpus of programs. And like if there was any question about whether a certain thing might make things slower in some cases, you would certainly do that. In this case, this thing we're doing, it's never better to have it be the way that it was. That was just, introductory code to get us to a working compiler. So, at some point I'm not that worried about being statistically robust testing across a lot of things. Of course, the tweakier your optimizations are, then you have, like, if you're tweaking with like code generation, then you absolutely have to do that, right? Because code generation, it's hard to say that there's one right answer for every case. But for this kind of stuff, this is just super low hanging fruit code optimization. So I wouldn't worry about it that much. Okay, we got more modify 8Bs. I bet they're not that hard to find. Oh, there's some modify 4Bs. Maybe if the modify 4Bs are easier to find, then maybe we just attack those. Modify 1B, 1B, 1B. It's a lot of 1Bs, bro. 4B. Maybe we hit the 4Bs, because that's what we're seeing right now. Modify 1B, 1B, 1B. Do we actually call that in lambda body print disassembly? Oh, we do this for all these branches. We might do a thing where we emit C moves instead of branches, because that's probably faster, certainly in terms of code generation. Let's write that down. Because we output several instructions. So here, anytime we generate a branch, we happen to know, due to the code that we're outputting, that the distance between one part and another of the branch is short, and so we know it's 1 byte. So instead of saying byte storage branch B, byte storage branch A, yeah. Okay. I said I was going to do the 4s, and now I'm just doing the 1s. Yeah, we'll see. We have 385,000 1s. We're just cutting down on explicit 1s right now. So and even like these lengths, we don't need those, but we'll change them one at a time. So byte storage branch A will do oh. We need to do all of these. Char branch a byte. And we need to just assign this all the time. JCC relative 8. Oh, they're all JCC relative 8. Do we have to return something? Nope. So branch a byte is going to be set there. And byte storage branch A. And then this is branch B byte there. So we already did that. But we need a JCC relative 8. Okay. And then let's just make sure that happens. Whoops. Let's go to release build. Look how long C++ takes to compile. It's just a tiny change, man. All right. So we didn't really change anything yet. Just making sure I didn't screw it up real bad. Okay. So branch B byte. Instead of modify 1b, we say star branch a byte equals let's make these just because there's this confusion about whether char is signed or unsigned in various compilers because nobody was organized back in the old days. Like, no one's going to care if it's signed or unsigned. You just write your program. It doesn't matter. Doesn't matter. Actually, it matters. Wow, we just got a 111 right there when we compiled. We're not even done yet, dude. Okay, so branch A byte gets set. Branch B byte gets set. This is branch B byte minus branch A byte, right? So then we don't need the lengths at all. Look at those 111s we're rolling. We are rolling through the whatever. We're rolling. Bro, this is great. Okay, so we don't need it's also going to just be less confusing without all these variables flying around. All right, did I delete something I need? Nope. All right, so post branch B, byte storage branch B. Whoops. No. Post branch B. That's what we care about. I almost screwed up right there. And then join. It's like, eh. Are you serious? Wait. Okay. Bro, we don't actually keep the length. Okay. All right. Because at the top of the loop, we did an ensure space 64 or more. These pointer differences are valid, and we don't need to do slow concatenator walking stuff. Okay, so like this is calling a big loop ass thing. Holy crap, dude. There's a bunch of this in the code. We're gonna be making it better. Output dot last point branch B distance is join minus post branch B. Looks good to me. No, it doesn't look good to me. Byte storage branch B, undeclared identifier. Oh. Did I really not ever do that? Hope I didn't screw it up real bad. We didn't check in nothing intermediate. All right. We're just changing like every branch in that program. It's no big deal. No big deal. Okay, so one thing that I was unhappy about this before was like with the proliferation of all the variables, it was like hard to understand, but you know, we're just going to trim down on the temporaries, right? This is easy to understand now. Like that I could live with. If I didn't break it. If I broke it, I can't live with it. 111, 112, 110, 110, 112. Bro, we're getting better. We're getting better. I'd call that 111. We started at 165. We're at 111. That's not too bad. All right. Optimize x64 backend branch emitting. Okay. Now what? Well, we're still going to see a lot of modify. I just picked a random modify 1B, and this one looked like something that happens a lot. But let's look for some other ones. Duplicate array, that's not that common. Logical not, yeah. Let's anywhere we do this pointer differencing, we're going to tag it with pointer difference to explain that really it is only valid because of this thing, okay? So logical not. What did we call it? Branch A byte. That's weird that it's called byte. Yeah. We're going to do that. Jump relative 8. Let's do it this output dot post branch A. You get branch B byte, branch B. Oh no! Don't screw this up. Oh, these are U8s here, in theory. Are these signed or unsigned jumps in x64? Oh, I think they're signed. It's just modify wanted a U8 for 1B, that's all. Whoops. Okay. Hope I didn't screw that up because I did it all at once. We need, I think, JNE relative 8. Yeah. Let's just do this one too. Actually, bro, if you're just going to call JCC relative 8, then just call that. Call it. I could have broken this real bad because it's late. Getting a little tired. Getting a little tired. Getting a little tired, but I can still run around in the lizard land and have some energy beams. All right. Great. That's just for logical knots, which, you know, there's going to be some number of those in the program, but, you know, not as many as branches, that's for sure. What was the first language I learned? Basic on the Commodore VIC-20. Commodore VIC-20 Basic, bro. It's how the real hackers style. $4K of RAM, actually less. I forget how much actual usable RAM you had while Basic was running, but it was not much. Mentally mutilated beyond hope of regeneration. Yes. Very sad. I wouldn't want to program in Basic today, but someone asked what I learned first, so there you go. Okay. Array bounds check. There could be a lot of these. You know what? I think I leave it off here because I'm starting to get tired. We're making good progress. Let's run a final telemetry build so that we know where to pick up tomorrow. We're just going to be attacking these modify 1Bs and 4Bs and 8Bs. All the killer bees. Right? 12:06 a.m. Saturday. How time flies. So modify 1B, we've still got 360,000. So yeah, I think we got rid of about 20,000 of those. So not a lot. 8Bs and 4Bs, right? So 20,000 8Bs is actually 160,000 of these. So maybe we attack the 8Bs next tomorrow. And then we attack the 4Bs because that's 160,000. That's 120. Wait, 160. 100. Yeah. Anyway, whatever. That's like almost, this is 320 plus thousand out of 360,000. So actually, I probably shouldn't have been chasing the modify 1Bs there. I should have just hit these. Because by the time we hit these, the number of these is going to be an order of magnitude smaller. So this will be down to like 5 milliseconds, which is still a long time. Don't get me wrong. But we won't we'll have saved almost the entirety of this. So we will have saved 20 plus 15, 35 plus 45. We'll have saved 80 milliseconds if we do that tomorrow. So that's a 0.08. So that, if we save that 80 milliseconds, right? So right now, when we compile release build, we're at like 111, 115. That'll bring us down to like 103 to 107, which is starting to get under 1 second again. All right, which is starting to be a respectable neighborhood. Not a good neighborhood yet. You're not talking Beverly Hills or Brentwood yet, but Los Feliz or something, So, yeah. Is there a competing metric that concerns me? Competing metric to what? What is that question? What is the maximum memory footprint of the compiler? I don't know, and I don't really care right now. We're not optimizing for memory. We're optimizing for speed. It ain't Skid Row. That's true. Better than Soma? Yeah. Yeah, Soma is pretty rough these days. Telemetry probably wouldn't know the maximum memory footprint unless I instrument my allocations, which I don't right now. It feels like it's longer than a second. Well, it is longer than a second. It's 1.1 seconds. Time it. Go back to the VOD and time it. It's 1.1 seconds. Will the compiler be able to compile itself on 32-bit machines? We don't support 32-bit right now. That's not a long-term limitation. We're just doing that for development speed right now. And, but frankly, I don't know if we will support 32-bit. I think whether we do that comes down to like whether there's a big demand for it from the embedded community. But in terms of compiling stuff on PCs and consoles and phones, you want 64-bit pointers these days. That's just how it is. So, yeah. Would this compiler be able to compile itself on 32-bit machines? Probably not. It's just not. That's just not something we're trying to do. Like, it would overcomplicate the compiler to try to make it always run in less than 2 gigs of RAM or whatever. It's just, that's not forward looking. You would rather take that complexity budget and spend it on something else. Isn't there a lot of overhead from timing 300,000 zones? Yes. So that's a good point, is we wouldn't save quite as much as these numbers say, but the amount of overhead is not that big because it's, the telemetry version of the whole game is 1.3 seconds. So, and we're running here in 1.1. So, it's 20% or less. That said, a lot of that could be focused in these, and so these could be more than 20%. It's possible. This is it's just an estimation when I say this is how much we'll save, right? We'll see how much we actually save when we save it. But I'm pretty glad we're down to like 111 from 165. So we saved 0.54 seconds today. That's good. I mean, it's not surprising at all because we've been letting it pile up, but it's good. What if you want to ship your game to Xbox 360? You're going to have a hard time because Microsoft won't let you. When you compile 64-bit, you have SSE2, which is nice. That's true. Is this eventually going to be open source? Eventually, yes, but not too soon. We can switch back and forth. I'm using LLD right now. It's actually LLD and the Microsoft Linker are about the same speed, I'm finding. People say LLD is faster, but for what we're doing, it's about the same speed as Microsoft Linker. Maybe a small difference. Are we linking to D3, D11? We probably are for something. I don't know. We're using some library. Oh, the shader compiler. I don't know why we're linking the shader compiler. Probably because we're linking a library that cross compiles to different shaders or something. We did good today, though. Thank you. Thank you for hanging out with me while I do my first compiler optimization in a long time. We'll do some more tomorrow because it's been fun and it's been productive. We'll see if we can get under 1 second tomorrow. You know, we're gonna be slowly shrinking this. So this thing right here is us making the output executable, or the output.obj file. And then this here is us just waiting for the linker to run here. So we're going to try to make this smaller than it is. It's 238 milliseconds right now. After we do all these dumb buffer things that are slow, we may then attack the type table. Because like I said, that'll make this one smaller and some of this smaller because we put it there and then we pull it out of there and whatever. So that could save us really a lot of time. That's a little more questionable because, like I said, there is a recursive data structure traversal that has to happen, but we could recurse and pack at the same time. And so you wouldn't necessarily add any cache misses by doing that. Although you might, I mean, if you recurse down far enough and then came up, you might be out of cache. I don't know. I don't think that would happen very often. Yeah. You would need the prefetcher to do a good job. But I think it would. Aside from developers, you win on architecture ideology. Do I have some performance or ease of use goals in mind? You can watch the speeches, you know, watch the one I did in Barcelona this year or the one from Croatia last year. It's 2 hours of me talking about this compiler and why it's going to work. Maybe someone can link it to you in the chat. Are we doing memory mapped IO? I don't think so. I think I just allocate memory and load a file in. It doesn't matter because reading and writing files is not that much time for us. Like, it takes us 5 milliseconds to write the obj file. That's not zero, but out of 1 second, that's tiny. And for reading files, similar, and it's also parallelized. Not sure, but this comes up on YouTube. Yeah, that's the Barcelona talk from this year. That is the most recent discussion. So if you watch that, you'll have some idea of what's going on here and why I'm doing it. And there's an older talk from Croatia as well. Let's see if we can raid somebody. Who is doing programming this late? Co-op open world RPG. Lurk Zone. Why is Cannabis Microgrowery? I guess maybe they're actually programming that. It's always up here. Programming, and I forgot to change the status. Python programming. Is anything really standing out? Let's do this 3D stuff. Action RPG, someone says. I'm not seeing a lot of serious programming. Leland, we could do Leland again. Go with the EE stream. Wait, what's the EE stream? EE. I have 9 matches for EE. And because it's a web browser, I can't see the actual matches. I don't know. What is programming? And I forgot to change the status. What is this one?
I don't want that. Play track ID. You're gonna have to get the current track, right?
Alright, well, the music is a little annoying. I don't know if this dude knows English. Oh, chat is in English. Alright, we'll raid.
1 second, let me think.
Oh yeah, we'll raid Felix. Alright, thanks everybody for coming by.
Let me check the objective handler.
And I'll see you later. Tomorrow.